Welcome! In this session, we'll dive into LeetCode problem number 463, Island Perimeter. This is a fascinating problem that challenges us to compute the perimeter of an island represented in a grid. We'll explore the problem step by step and discuss potential solutions, starting from a brute force approach. Let's get started. The island perimeter problem is about calculating the perimeter of an island within a rectangular grid. In this grid, each cell is represented by either a 0 or a 1, where 0 stands for water, and 1 represents land. The land cells are connected either horizontally or vertically, but not diagonally. It's important to note that the grid is entirely surrounded by water, and there is exactly one island composed of one or more connected land cells. Additionally, the island does not have any lakes, meaning there is no water trapped entirely within the island that isn't connected to the outer water. The task is to calculate and return the total perimeter of this single island based on the given grid input. The output for this problem is a single integer representing the calculated perimeter of the island. To clarify the problem further, let's look at an example. Suppose the input grid is a 4x4 matrix as follows: 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0. The output for this grid is 16, which represents the total perimeter of the island formed by the land cells. The goal is to correctly compute this value based on the arrangement of land and water cells in the grid. To understand why the perimeter is 16 in the first example, we visualize the grid where 1s are land cells and 0s are water. Each land cell contributes 4 to the perimeter initially, but when 2 land cells are adjacent, they share an edge, reducing the perimeter by 1 for each shared edge. In this grid, the island has several adjacent cells, so the shared edges are subtracted from the total. When we sum contributions from all land cells and adjust for shared edges, the final perimeter value is 16. This approach ensures that we account for both individual contributions and overlaps between cells. In the second example, the input grid is a single-cell grid, 1. Here, the island consists of only one land cell, and since it has no adjacent land cells, it contributes the full 4 to the perimeter. The output is therefore 4. This case highlights how a single isolated land cell behaves in terms of perimeter calculation, as there are no shared edges to adjust for. In the third example, the grid is 1, 0. This time, the grid has one land cell and one water cell. Since the land cell does not have any adjacent land cells, it contributes 4 to the perimeter directly. The water cell does not affect the calculation because it does not contribute to the island's perimeter. The output is again 4, emphasizing that only the land cells are considered for perimeter calculation, and the contribution is reduced only when adjacent land cells exist. Finally, let's discuss some edge cases. The smallest possible island is a single land cell, such as in the grid 1, where the perimeter is 4. An all-water grid, like 0, is invalid because the problem guarantees there will always be exactly one island. Another edge case is a large grid, such as a 100 by 100 grid filled entirely with land cells. This tests the solution's efficiency at scale, as the perimeter would involve significant computation to account for shared edges. These cases help ensure that the solution is robust and performs well under various conditions. To solve the island perimeter problem, we first considered two approaches. The brute force approach is quite intuitive. We go through every cell in the grid. For each land cell, which is represented by the value 1, we check all 4 of its neighbors up, down, left, and right. If any of these neighboring cells is water, represented by the value 0, or if the neighbor goes out of the grid's bounds, it contributes to the perimeter. While this method is simple and easy to understand, it involves redundant checks for each cell, which makes it inefficient. The time complexity here is O, n asterisk m, where n and m are the grid dimensions, and the space complexity is O, 1, since we don't need additional data structures. Now, the optimized approach, called adjacency counting, builds on this by reducing redundant checks. The key realization is that each land cell inherently contributes 4 units to the perimeter, but when 2 land cells are adjacent, they share sides, which reduces the perimeter. So, for each land cell, we add 4 to the perimeter, and for every pair of adjacent land cells, we subtract 2 from the total perimeter for each shared side. This avoids double counting and makes the algorithm more efficient. The optimized adjacency counting approach can be implemented in a few simple steps. First, we iterate through all the cells in the grid. For each cell that is land, we add 4 to our perimeter. Then, instead of checking all 4 neighbors, we only focus on the right and bottom neighbors. If either of these neighbors is also a land cell, we subtract 2 from the perimeter for each shared side. This ensures that we don't perform redundant calculations, as we only account for shared sides once. Finally, after processing all cells, we return the total calculated perimeter. The efficiency of this method is clear when we break down its complexity. The time complexity remains O and *m, because we still visit each cell once, but now we avoid unnecessary checks. The space complexity remains O1, since no extra data structures are used. The most important insight here is recognizing that every land cell has a fixed contribution of 4, but shared sides reduce the total by 2. By focusing only on right and bottom neighbors, we streamlined the calculations without losing accuracy. When deciding on the best approach, we chose adjacency counting over brute force for several reasons. While the brute force method is straightforward and easy to code, it is far less efficient because of its redundant neighbor checks. On the other hand, adjacency counting eliminates these redundancies by leveraging the fixed contribution of each land cell and adjusting for shared sides in a systematic way. This makes it both time efficient and relatively simple to implement. Of course, there are trade-offs. The brute force method's simplicity makes it appealing for smaller grids or as a first step in understanding the problem, but its inefficiency becomes evident as the grid size increases. The adjacency counting method, while slightly more complex, achieves optimal time complexity and handles larger grids much more effectively. Given the constraints of the problem and the grid-based nature of the solution, adjacency counting strikes the right balance between simplicity and performance, making it the most practical and efficient choice for this problem. To solve the island perimeter problem, we begin by understanding the task at hand. We are given a 2D grid that represents a map, where each cell is either land, represented by 1, or water, represented by 0. The goal is to calculate the perimeter of the land, considering that each land cell contributes to the perimeter based on how many of its sides are adjacent to water or are at the grid's boundary. The algorithm starts by initializing a variable, perimeter, to 0. This variable will be used to accumulate the total perimeter as we process each land cell. We then use 2 nested loops. The outer loop iterates through each row, while the inner loop iterates through each column within those rows. This structure ensures that every single cell in the grid is visited exactly once. As we traverse the grid, we check if the current cell is a land cell by verifying if its value is 1. If not, we simply skip that cell and move to the next one. This setup allows us to focus only on the land cells, which are the ones contributing to the perimeter. Once we identify a land cell, we calculate its contribution to the total perimeter by examining its 4 neighbors, the top, bottom, left, and right cells. For each neighbor, we check if it is either out of bounds or contains water. If the neighbor is out of bounds, it means that side of the land cell is at the edge of the grid and contributes to the perimeter. Similarly, if the neighbor contains water, that side of the land cell also adds to the perimeter. For example, if the top neighbor at I1, J, is out of bounds or contains water, we add 1 to the perimeter. The same logic applies to the bottom neighbor, I plus 1, J, the left neighbor, I, J1, and the right neighbor, I, J plus 1. By summing these contributions for each land cell, we ensure that all edges adjacent to water or the grid boundary are accounted for. After processing the neighbors, the computed contribution for the current land cell is added to the perimeter variable. Once all cells in the grid have been processed, the total value of perimeter is returned as the final result. This approach ensures that we accurately calculate the perimeter of the land, considering both internal and boundary edges. This algorithm is efficient because it avoids redundant computations and processes each cell in constant time. Specifically, the time complexity of the algorithm is O, m*n, where m is the number of rows and n is the number of columns in the grid. This is because we traverse the entire grid exactly once. Additionally, the algorithm handles edge cases gracefully. For instance, if the grid is completely empty, meaning all cells are water, the perimeter will correctly be 0. If the grid contains only land cells with no water, the perimeter will equal the outer boundary of the grid. For example, a 3x3 grid of all land cells would have a perimeter of 12. Similarly, a single land cell in isolation will return a perimeter of 4, as all its sides are exposed to water. The algorithm also uses minimal data structures. The 2D grid serves as the input, allowing direct access to any cell using its row and column indices. The output, perimeter, is stored in a single integer variable, making the solution space efficient. The key operation in this algorithm is the neighbor check, which is performed for each land cell. This involves checking the bounds and values of the 4 neighboring cells, top, bottom, left, and right. Each of these checks is constant time, or O1, making the algorithm efficient. The boundary conditions are particularly important here to ensure that out-of-bounds indices are handled correctly. For example, when checking the top neighbor of a cell in the first row, the algorithm ensures that it does not attempt to access an invalid index. Similarly, for a cell in the last row, the bottom neighbor is carefully checked to stay within bounds. In terms of space complexity, the algorithm is highly optimized, using only O1 additional space. All computations are performed directly within the input grid and the perimeter variable, without requiring any auxiliary data structures. The pseudocode provided here outlines the first part of the algorithm, including the initialization of the perimeter variable and the nested loops for iterating through the grid. For each land cell, the checks for the top and bottom neighbors are performed, and their contributions are added to the perimeter. The pseudocode continues with the checks for the left and right neighbors of each land cell. If the left neighbor at ij1 is out of bounds or contains water, 1 is added to the perimeter. Similarly, if the right neighbor at ij+1 is out of bounds or contains water, another 1 is added to the perimeter. After all 4 neighbors have been checked for a particular land cell, its total contribution to the perimeter is fully computed and added to the perimeter variable. Once all cells in the grid have been processed, the final value of perimeter is returned as the result. This completes the algorithm, which is both efficient and straightforward. The clarity of the logic, checking each neighbor in constant time and accounting for boundary conditions, ensures that the algorithm is robust and performs well across different types of input grids. Whether the grid has isolated land cells, continuous blocks of land, or a mix of both, the algorithm accurately computes the perimeter using this systematic approach. This solution efficiently calculates the perimeter of an island in a grid. The function takes a 2D grid as input, where 1 represents land and 0 represents water. First, it initializes the grid dimensions, rows and calls, and a perimeter variable to store the calculated perimeter. Next, it iterates through each cell in the grid using nested loops. If a cell contains land, value 1, it initially adds 4 to the perimeter, assuming it is completely surrounded by water. The function then checks for adjacent land cells. If the cell above, R1, is land, it reduces the perimeter by 2, as this edge is shared. Similarly, if the cell to the left, C1, is land, it reduces the perimeter by 2 for the shared edge. This process ensures every shared boundary is only counted once. Finally, the function returns the total perimeter after examining all cells in the grid. This approach effectively handles edge cases, such as islands touching the grid boundary or multiple disjoint islands, while maintaining a time complexity of O(m*(n), where m and n are the grid dimensions. This is the Java implementation of the island perimeter problem using the same logic as the provided Python solution. It calculates the perimeter by iterating through each cell in the grid and adjusting for shared edges with neighboring land cells. Key differences include explicit type declarations, use of Java arrays, and the overall class structure typical of Java syntax. Here, we're tackling the simplest case, a single land cell. Our input grid is a 1x1 matrix containing just one land cell, represented by the value 1. To begin, we initialize the number of rows and columns as 1, and set the perimeter to 0. Now, we start iterating through the grid. At row 0, column 0, we find a land cell, so we add 4 to the perimeter, making it 4. Next, we check its neighbors. The top neighbor doesn't exist because row -1 is less than 0. Similarly, the left neighbor doesn't exist because column -1 is less than 0. Since there are no other cells in the grid, our iteration ends, and the total perimeter is 4. This matches our final output. Now, we have a row of 3 land cells. The input grid is a 1 by 3 matrix, and we again initialize rows and columns as 1 and 3, respectively, with the perimeter starting at 0. As we iterate, at row 0, column 0, we encounter a land cell and add 4 to the perimeter, making it 4. There's no top neighbor since row -1 is less than 0, and no left neighbor since column -1 is less than 0. Moving to column 1, we find another land cell and add 4, increasing the perimeter to 8. However, this cell shares an edge with the land cell at column 0, so we subtract 2, reducing the perimeter to 6. At column 2, we find one more land cell, add 4, bringing the perimeter to 10, but subtract 2 for the shared edge with the land cell at column 1, leaving us with a final perimeter of 8. This is the value we return as the output. Here, we examine a square island, represented by a 2 by 2 grid of land cells. We start by initializing rows and columns as 2, and the perimeter as 0. As we iterate, at row 0, column 0, we find a land cell and add 4 to the perimeter, making it 4. The top neighbor doesn't exist because row -1 is less than 0, and the left neighbor doesn't exist because column -1 is less than 0. Then, at row 0, column 1, we find another land cell and add 4 to the perimeter, making it 8. However, this cell shares an edge with the land cell at column 0, so we subtract 2, reducing the perimeter to 6. Moving to row 1, column 0, we find another land cell and add 4, bringing the perimeter to 10. This time, there is a top neighbor at row 0, column 0, so we subtract 2 for the shared edge, leaving us with a perimeter of 8. Finally, at row 1, column 1, we encounter the last land cell in the grid and add 4 to the perimeter, making it 12. This cell has a top neighbor at row 0, column 1, so we subtract 2 for the shared edge, reducing the perimeter to 10. Additionally, it has a left neighbor at row 1, column 0, so we subtract 2 again for that shared edge, leaving us with a final perimeter of 8. The iteration is now complete, and we return this value as the output. This demonstrates how shared edges between adjacent land cells systematically reduce the overall perimeter. To analyze the time complexity of this algorithm, we start by considering the grid's dimensions, which are defined as rows by cols. The algorithm processes each cell in the grid through a nested loop structure. The outer loop iterates over the rows, and for each row, the inner loop iterates over the columns. This results in rows *calls total iterations, as every cell is visited exactly once. For each cell, the operations performed are constant in nature. Specifically, we check if the cell contains land, which is an O1 operation. If it is land, we add 4 to the perimeter and then check the top and left neighbors, adjusting the perimeter for any shared edge. Each neighbor check and perimeter adjustment is also an O1 operation. Since all of these tasks take constant time per cell and the algorithm processes all cells in the grid, the overall time complexity of the algorithm is O rows *calls. Next, let's consider the space complexity of the algorithm. The memory usage is determined by the number of additional variables and data structures required. Here, the algorithm uses only a few integer variables, such as rows, calls, and perimeter, which together require constant space, or O1. It does not create any auxiliary arrays or modify the input grid, meaning no additional memory is allocated for data structures. Therefore, the space complexity remains O1. When analyzing best, average, and worst-case scenarios, the time complexity consistently remains O rows *calls. In the best case, where all cells are water, the algorithm still visits every cell once. In the worst case, where all cells are land, it performs extra neighbor checks for every cell, but these are constant time operations. Even under average conditions, where the mix of land and water varies, the algorithm still processes each cell exactly once, maintaining a time complexity of O rows *calls. Now, let's compare this optimized algorithm with a brute force or naive approach. A brute force method might involve iterating over all land cells and their neighbors multiple times, redundantly checking shared edges between adjacent cells. This inefficiency could lead to a higher time complexity, especially if the implementation doesn't account for avoiding repeated neighbor checks. In contrast, the given algorithm optimizes this process by checking only the top and left neighbors of each cell. By doing so, it ensures that each shared edge is accounted for only once, avoiding unnecessary duplication. This optimization results in a time complexity of O rows asterisk calls, which is optimal for this problem. Mathematically, we can verify this by noting that the nested loop structure ensures all rows asterisk calls cells are visited once, and the constant work per cell means the overall time complexity is O rows asterisk calls. Additionally, since the algorithm uses a fixed number of variables without allocating extra memory, the space complexity remains O(1). This efficiency makes the algorithm highly suitable for the problem's constraints. When solving the island perimeter problem, there are some common mistakes to watch out for. First, not accounting for edge cases can lead to incomplete solutions. For instance, grids with no land at all, where everything is zero, or grids that are entirely land with all ones, can often be overlooked during implementation. Missing these edge cases means your solution might fail specific test scenarios, especially in interviews. Next, incorrect bounds checking is another frequent issue. When checking a cell's neighbors, whether it's up, down, left, or right, you must ensure that you're staying within the grid's boundaries. Failing to do so can result in runtime errors or undefined behavior, which is something you definitely want to avoid. Another mistake is inefficient iteration across the grid. This happens when you repeatedly visit the same cell without marking it as processed, leading to unnecessary computations. This is particularly problematic in larger grids, as it can significantly increase the time complexity. Finally, confusion between breadth-first search, BFS, and depth-first search, DFS, is a common pitfall. For example, mixing up the iterative or recursive logic of these traversal methods can result in incomplete or incorrect solutions, especially for problems like counting islands or calculating perimeters. Understanding these typical errors can help you debug and refine your approach more effectively. Now, let's talk about space optimization and some key insights for interviews. One common mistake developers make is not optimizing for space complexity. For example, using an extra visited array to track processed cells isn't always necessary. You can often modify the grid itself to serve this purpose. This approach reduces memory usage, which is especially important for handling large grids efficiently. Shifting to interview-specific strategies, it's crucial to break down the problem systematically. Explain your plan for traversing the grid, checking neighbors, and managing visited cells. This demonstrates clarity in your approach. Be prepared to discuss trade-offs, such as when to use BFS versus DFS. BFS uses a queue and is level by level, while DFS relies on a stack or recursion. Each has its advantages, and understanding their space and time implications will make you stand out. Optimization opportunities are another area to emphasize. For example, you can explore ways to avoid redundant checks or implement early termination in scenarios where the solution is already determined. Finally, clear communication is key. Make sure you articulate your thought process, especially around handling edge cases or boundary conditions. This not only helps the interviewer follow your logic but also showcases your problem-solving skills. There are also several related problems that you might encounter, which share similar patterns with the island perimeter problem. Some examples include LeetCode 200, which focuses on counting the number of islands, and LeetCode 695, which calculates the maximum area of an island. Of course, LeetCode 463 itself is directly relevant, and LeetCode 733, which involves flood-fill algorithms, is another excellent practice problem. Beyond these, it's worth exploring alternative approaches to solving grid-based problems. For instance, using disjoint set union, also known as union find, can be an efficient solution, especially for problems that involve multiple queries, like counting connected components. However, this method can be more complex to implement compared to DFS or BFS. Its overall complexity includes O, n*m, for traversing the grid and an additional O, alpha, n, for the union find operations, where alpha is the inverse Ackermann function. Another approach is iterative DFS using a stack. This avoids issues with recursion depth in languages that limit stack size but requires you to manage the stack manually. Both of these methods offer unique trade-offs based on the problem constraints and requirements. Finally, two additional approaches to consider are breadth-first search, BFS, and dynamic programming. BFS ensures a level-by-level traversal of the grid. This can often feel more intuitive, as you process each neighboring cell systematically, but it does come with the trade-off of requiring extra space for the queue. This additional memory overhead can become significant in larger grids. On the other hand, dynamic programming can be a powerful tool for certain grid-based problems, particularly those involving counting paths or optimizing state transitions. However, in basic traversal problems like island perimeter, it's generally less applicable since the focus is more on immediate neighbor relationships. Each of these techniques has its strengths and weaknesses, so understanding the problem requirements will help you determine the most suitable approach. Great job making it to the end. To summarize, we tackled the island perimeter problem and explored how to calculate boundaries in a grid. Remember, understanding efficient grid traversal and handling edge cases are key skills for similar challenges. Thanks for watching, and don't forget to like and subscribe for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!